Hello everyone. Today class we see about how to design binary to gray converter. Okay, so before we going to design, we see the symbol and truth table of the binary to gray converter. Okay, this is the symbol. So B0 to B3 is the binary values, and that will convert to the gray value. Okay, so how it will be converted by using the XOR gate. So this is the truth table for the binary to gray converter. So if you see, this is the binary code and this is the output of the gray code. Okay, so now we design the binary to gray converter. Okay, we're going to design binary to gray converter in ESC design suite 14.7 Xilinx. Okay, so we're going to design binary to gray converter in VSGL code. Okay, so this is the project navigator. So we're going to design the binary to gray in this platform only. So first click file. In this file just click the new project. So here we want to give the file name. Just I'm going to give binary to gray. Okay, so click next. Here we want to choose the FPGA device and speed and the language, which language we're going to use. We're going to use the VSGL code. Okay, so I'm selecting the VSGL language. Click next, finish. So the file will be developed. In this file we're going to add the source file, right? So we want to add by using the new source. Just click the VSGL model we're going to use. Here just give the binary gray, just click next, and here we want to give the input and output values. So if you see the symbol means we going to use 4-bit. So B0 to B3 is the input value and G0 to G3 is the output value. So just give B input, G output to 3, 0 to 3. So we're going to use 4-bit. Okay, so 0 will be the lowest significant bit and M will be the most significant bit. Okay, so that's finished. So this is the library function and this will be the input and output. So here we're going to develop by using this circuit. So G output will be the B3. So just give T3 equal to B3 semicolon. After that G2 will be the B3 XOR B2. G2 will be the B3 XOR B2. Next G1 will be the B2 XOR B1. Next G0 will be the B1 XOR B0. So this logic gate XOR gate that will be already in the predefined, because full and full Xilinx software are developed for the VLSI only. So logic is very basic. So all the logic gates, XOR gate, OR gate, NOT gate, NAND gate, all the gate will be already pre-defined. So we can just use the correct logic gate in the by checking the circuit diagram. Okay, so B1 XOR B0, so end behavior. Okay, so just save, and we want to check whether we did any mistake in this code. Okay, let's check the syntax. If we mistakenly we didn't give any semicolons, we didn't use properly, then means error will be occurred. So here we did one mistake. What means we are using B and G in the array form, so we want to give that in array mode. Okay, so now we change the code and we check, so there is no any error. So now we check the RTL schematic. Okay, in this RTL schematic we can able to come the circuit diagram. Okay, so RTL schematic and technology schematic are the we can able to check LUT tables and the circuit diagram of this code of this binary to gray converter design. So if you click OK and check means, so we using XOR gate, 3 XOR gate we using, right? So 1 2 3, so we design is right. Next we want to check the LUTs, how much LUTs we using. So we using just 3 LUTs. If you check LUTs means here we can come to know that we using XOR gate, AND gate and OR gate. So obviously this is the XOR gate, right? So we using 3 XOR gate. If you just click the LUTs means you can able to check the equation, truth table and the K map. So after check the schematic and the technology schematic, next we want to know area, power and delay. We want to check these 3 parameter whatever the design may be. So we want to modify it, or we going to do any conversional means we want to check this one, because we want to design any circuit in VLSI means these 3 parameters is important to check area in synthesis report. So how much LUTs we using, how much input output we using, how much buffers we are using, that and all the area comes under the area. Okay, so delay will be the 7.824 nanosecond. Okay, so next we check the power, static power in the place and route analysis power distribution. This will be analyzed in Xilinx power analyzer. Okay, so for that we want to translate and we want to map and we want to place and route the code. Okay, so if you keep the speed in -5 or like that means, then this running process will be will be speed will increase. Okay, if you keep in kept in -2, like that means then the process of running will be very low. So that power supply will be 0.060. Okay, so next we develop the test bench. So just click new source and VSL test bench and give the binary to gray -tb, like that. Develop the file name, click next and finish. Why we going to develop the test bench means we know we want to check this code with the truth table, right? We want to develop, so for that we want to give the input values and clock timing. So already there will be the pre-defined clock timing, that and all we want to remove. So here just give B will be the input, right? Just give the input, okay, and the time delay. So I'm giving just 3 parameters, like that only input. So just save and run and see whether there will be any error in this code. So I'm giving input 00, 01, 0011, 0101. Okay, so there is no any error. Then the window will be open. Okay, so simulation window will be open. Here we want to check it's giving the right output or not. So if you check means 000, 001 means 001 means 001, 010 means 0011, right? 0011, then the 0011, 0010, 0010, 0101 means 01, 01 means 0111, 0111. So the truth table also right, the designed RTL schematic also right. So we designed the binary to gray converter. Okay, so next class we see gray to binary converter. Okay, so today class we check the area power delay of the binary to gray and also check the simulations output. Okay, thank you.